Okay, so let's look at how we get a sizable amount of energy out from nuclear fission. Here we have our uranium nucleus. Now I'm not going to draw all the little neutrons and protons that would be inside this. It'll just take too long. So we just draw the nucleus of uranium. And here we have the little neutron we use to make it undergo fission. Okay, when that happens, this splits in two, forming those smaller daughter nuclei, and releases an amount of energy. But if that's all that's happened, we wouldn't notice it. However, what also happens here is it releases two or three neutrons. Now, if we take those neutrons and get them to hit in and get absorbed by three more uranium-235 nuclei, and each of these splits into daughter nuclei. Okay, so each of these undergoes fission. We then will have 3 times as much energy in this phase than we did for the first fission reaction. However, this can continue, okay? So this is a chain reaction where the products from one nuclear reaction start the next nuclear reaction. And if this one releases 3 neutrons, now on average it's actually 2.5, but we can't really draw 2.5. This one also releases 3 neutrons. This one also releases 3 neutrons. And then each of those neutrons gets absorbed by a uranium nucleus. We can see in the next step, the time difference between these steps, you're talking nanoseconds. Okay, we then have times 9. Okay, still much bigger than the first one, still not sizable. If we continue that process, next step, I'm not going to draw it, we will have 27 times as much. Then 81. Those mathematicians could probably do this quickly in their heads, but I'll just use my calculator. 243. Next time we will have 729. Then about 2,000. Then about 7,000. Then about 20,000. Then about 60,000. Then about 170,000. Then about 500,000. Then 1.5 million. Then 5 million. Then 14 million. And that process, if we just let it continue in that way, the amount of energy that is released through this reaction with time increases exponentially. It just keeps getting bigger and bigger and bigger and bigger. And this is essentially a nuclear bomb. An uncontrolled chain reaction releases a huge amount of energy in a short period of time. The energy is released as heat, essentially, and causes a massive blast. Making a nuclear bomb is actually easy enough to do. The hardest thing is getting enough uranium. We say this has to be uranium-235. Most uranium is uranium-238. So the hard thing is actually separating the uranium-238 from the uranium-235 to get enough fuel for this. However, this shouldn't be what we want to do as physicists. Much harder is to actually control that reaction so it's nice and steady, and if we get a nice steady output rather than exponentially increasing output, we can then use the heat produced to produce steam, which can drive a turbine, which can turn a generator, which can generate electricity. If we want to do that, what we need to do here is, in the first one, where these 3 neutrons go on to produce another fission reaction, we don't. We just let one do it. And then all these subsequent reactions don't happen. In the next step, we don't let these ones continue. And then we will just get one fission, one fission, one fission, one fission, one fission. If we need to produce more electricity, we can increase it for a little while. So we can then maybe let 2 get absorbed, and that will increase the amount of energy being produced. But then we go back to just producing a steady amount again by blocking most of the neutrons that are produced and only letting one from each reaction start the next reaction. That way it doesn't decrease, but it also doesn't increase the amount of energy being produced in time. Okay, so they are our chain reactions. I'm going to post another little video, but we'll talk more about how a nuclear reactor works, the positives and negatives of a nuclear reactor. We've done all this before in our energy topic. However, you should be able to understand it better now that we know how those nuclear reactors work.